before I forget. Anito, you had your hand up. You have the floor.
Yeah, so I had a quick question. I don't know what happened. So you know how like for some questions, like with the power series, it's like find R and then find the interval, but not interval of convergence, just like, when you like take the absolute value and all of that, how
Okay.
it's like, yeah. So I was doing the web work and I got my interval right, but I got my radius wrong somehow. And I don't know what the deal was.
Oh, okay. If you have time, well, I guess no, we don't have office hours today. So I would probably post it on Piazza, or if you can wait until tomorrow with office
Yeah,
hours, I'd be
yeah, I
happy
can,
to
yeah, for
take a look
sure.
at it.
If there was like, I don't know if there was like a specific case or something happened like that, but that's what happened to me and it was weird.
That is strange. Yeah,
Yeah.
I mean, if you have the interval, it should be pretty fast to get the radius. So
Yeah,
I'm
that's what I'm
surprised that there was
saying.
this mismatch. So,
Yeah,
yeah,
okay, for sure. Thank
okay.
you.
Yeah, no problem. And Ajuan, you have the floor. If you have a question still.
All right, can you hear me?
Yeah, sure can.
All right. I also had a question about the end explanation mark again. So when it comes to that, and when we like do the an plus one over an,
Okay,
how
yeah.
would they sub that in? Would it be like in parentheses n plus one, close the parentheses, and then the explanation part again? Because I always get confused when we should do these in like 11.6, I believe it was.
Yeah, I mean, you do have to simplify them. It's not true, for instance, you can't rewrite like n plus 1 factorial divided by n factorial. This would not be equal to n plus 1 divided by n factorial. So you can't like do some combination like that.
Mm-hmm.
But you can go ahead and write with this. This just says that it simplifies down to just n plus 1.
Okay, yeah, that's simple then. Okay, I got you. Thank you.
All right, super. Yeah, no problem. Okay, great. So why don't we go ahead and skim over the pre-class video notes really quick here. Again, we just did a proof for this thing here, right? This 1 over 1 minus x. In the video here, right, we had claimed that this was equal to this infinite polynomial or this power series, 1 plus x squared, so on and so forth. Of course, if you want to write it in the sigma notation, there it is. And we just did a proof, right, that showed that this is the case. So long as, right, you're kind of centered about 0 and your radius of convergence is going to be 1 in this case. It's kind of like the same thing for the geometric series, right? For the geometric series, right, we used to have like an A and an R down here. So this is definitely related to that. And before we said that the R had to be, the absolute value of R had to be less than 1. Here we have the absolute value of X has to be less than 1. Okay. So that's that. And then this is an entire section pretty much dedicated to what can you do with this information. And it turns out that you can actually get pretty darn far, surprisingly. So you can do things like this, right, where you don't have just a 1 minus x in the denominator, but you can do all sorts of interesting substitutions here, right? So if I substitute this x with 3x squared, and more formally, we could introduce u like we've done here in the videos and whatnot, right? Then you can go ahead and get a power series or an infinite polynomial for this, upgraded function here, the one with the 1 minus 3x squared in the denominator. And of course, your radius of convergence is going to be changing as well. And so you can always kind of find that out. Again, just kind of by using this information that we had, that the absolute value of, in order to use this fact right here, the absolute value of u now needs to be less than 1. That is, the radius of convergence for u would be 1. And so if you want to know what that translates to for your x, right, you can just plug in your substitution, in this case 3x squared, and rewrite a little bit to get your radius of convergence for x. And you can do all sorts of things, right? So here we divided through by 3 and we multiplied by x. And so again, you can kind of see that you can actually get quite far. Better yet, this theorem right here says you're allowed to take derivatives or integrals across the board. And that is a legitimate thing to do for power series, right? So we can take derivatives, we can take integrals, and so we can create even more functions based off of this. So for instance, we have here the 1 over quantity, 1 minus x squared. And so by taking the derivative of kind of our original power series here, this 1 over 1 minus x, we can see that we can actually create a power series for this new function here. And this theorem right here goes on to say that if you take the derivative or if you take the integral, first of all, that's a legitimate thing to do. And second of all, your radius of convergence doesn't change. So you might be paranoid, right? Well, maybe it converges at a different spot or, you know, a different interval or whatnot. But this theorem right here is saying that you can take derivatives, you can take integrals, and your radius of convergence, your interval of convergence even, isn't going to change. And so that's quite nice. So we did a derivative one, and then here on this page, we did a couple integral ones. So we talked a little bit, right, that if you were to integrate 1 over 1 plus x here, right, you would get to kind of this natural log thing. And so by using that, right, we can come up with a power series for the natural log of 1 plus x. And so we did that, and we also saw that you can make something like tangent inverse, because this is just going to be the integral of like 1 over, well, we see here 1 plus x quantity squared plus 1. So again, the u's are getting a little bit more complicated, but what I want you to take away from this is that you can take derivatives and you can take integrals with your power series. And, you know, this is a legitimate thing to do. It doesn't ruin your equation by any means. All right, so those are the video notes kind of in a nutshell here. Any questions, comments, concerns, things before we move on to the new problems for today? Ajuan, I see that your hand is up. I'm not sure if this is just you forgot to put it down or if you actually have a question. So I'll give it a second before I call on you. Will, you just raised your hand. Do you have a question for us?
Yes. For 11.9.3, the second example, I was wondering why you multiply that whole function by x over 3.
So I multiplied it by x because there's an x up here that isn't in kind of our traditional 1 over 1 minus u, right? I'm basically trying to take what I have here and get it into this form, right? That looks like 1 over 1 minus u, because that's what I know an infinite polynomial for. Now, the other thing that I should mention is that x itself is already a polynomial, right? And so I don't need to rewrite it into, you know, an infinite polynomial or anything like this. It's really only this reciprocal function that isn't in its polynomial form. So that's the bit that we kind of have to work with for a little bit. So the first thing is, right, how do we get that 1 to turn into an x? So that's where we multiply by x. But actually that 3 right there was already there, and I just kind of factored it out because remember, I'm trying to make it look like this thing here. And here we have a 1. And that is very specific, right? That you need a 1 there. And so in order to get my function to look like this, I went ahead and I factored out that 3. So when you factor out that 3, of course, that 3 there becomes a 1. And then this one right here becomes x over 3. And when you factor it out, well, it's you know, you don't just delete it or anything like that. It's got to, you know, hang out off to the side probably.
Okay, that makes sense. Thank you.
Super. Yeah, no problem. All right. Let's just double check. Excellent. So let's do some new problems then here. So class problems. Again, last time we were always given a power series. This time we're going to be creating our own power series, right? So here's kind of, I have this broken down into very similar setups for web work and whatnot here. So it asks, what are the first 3 non-zero terms for the power series? Express it in, you know, a certain form here in the sigma notation. And quite often WebWork asks for what is the C sub n, right? What do the constants look like for the different powers of x? And then we can also go on to ask for what is the radius of convergence. So these are kind of the classic 3 questions for a problem like this. Again, what we're going to do is I'm going to take my f and I'm going to try to get it to look like you know, this one piece of information that we know, what 1 over 1 minus x is in terms of an infinite polynomial or in terms of a power series. So I'm going to go ahead and bring 6 off to the side here, right? 6 is technically a polynomial, right? It's a constant polynomial. It's a rather boring function there, but that's fine. And I'm going to rewrite this as 1 divided by 1 minus negative 4x. So again, the one thing that we have really for this section is that we know what this thing looks like in terms of its infinite polynomial. So this is going to look like 1 plus u squared plus u cubed plus so on and so forth. And if we were to write that in the sigma notation, that would be summing up from n equals 0 to infinity of u to the n, right? And if you were to plug in u equals 0, if you were to plug in n equals 0, you would get the 1 here. If you were to plug in n equals 1, you would get 1 to the first power. N equals 2, you would get u squared. And again, you're summing all these things up. So these are kind of the three representations maybe for this function. And I think it's very useful as you're doing these problems to carry all three of them along with you. And you'll see that there are different parts of this problem where you would want to look at maybe, one of these more than you would like to look at the others. Okay, so that being said, we can now see that in order to get the power series for my function here, we should let u be equal to this negative 4x. So u is equal to negative 4x. And so when we do that, right, we get our function, which is again the 6 divided by 1 minus, and I'm just going to go ahead and combine the minus and negative here and just write it as 1 plus 4x here. And this is going to be equal to 6 times, and remember, right, because this doesn't have the 6, so you do have to multiply 6 by everything. So that's where that's coming from. So you get 1 plus u, so it's going to be negative 4x, plus u squared, negative 4x squared, plus u cubed, negative 4x cubed, so on and so forth. And again, everything is getting multiplied by 6. And then if you wanted to write this in the sigma notation, again, you have to multiply everything through by 6. And we're going to be summing up. And instead of u, right, we're going to write this negative 4x. Negative 4x raised to the nth power. That's what my u is there. And n goes from 0 to infinity. Looks like I'm writing this a little bit too close to the edge here. Let me give myself a little bit more room, cheating using technology here. Because, yeah, that's really crammed. Negative 4x to the n. Okay, so we can see that really for like part A, we want the first 3 non-zero terms of this power series. This is going to be very useful because we have it all written out. And so I can just tell you what are the first 3 non-zero terms. And then for part B, right, that's where we're interested in maybe the sigma notation. And so kind of each one of these has, a use. And then, of course, we'll talk about the radius of convergence here. And so let's go ahead and maybe expand this out a little bit and simplify things. We have 6. Let's see, we have negative 4x. And of course, we need to multiply that by 6. So this is going to be negative 24x. And let's see, if I was to take negative 4x and square it, that would be positive 16x squared, right? Because when you take a negative and you square it, that becomes positive. And then I need to multiply that by 6, right? Everything needs to get multiplied by 6. So when I multiply 16 by 6, I think I get 96. And then, of course, right, this is going to continue on. You'd have to take negative 4 and cube it and then multiply that by 6. Notice that this is only asking for the first 3 non-zero terms. So if it asks for more than that, certainly we could figure them out. But the first 3 non-zero terms are 6, negative 24x, and then 96x squared. Those are the first 3 non-zero terms. So that's going to be my answer for part A. So maybe I'll just put here part A. We need to use this bit here. Now, this is already for part B, right? I'm now thinking about the sigma notation and everything. We're already quite close, but quite often, right, for these power series, you want to write it as, get all of your x's together as one piece and all of your numbers together as one piece, right? The C stands for coefficient, right? So this is the coefficient that's next to x to the nth power. So we want to get all of our coefficients, all of our numbers together, and then we want to get all of our x's together. And so I would recommend that we go ahead and write this. Well, first thing that we're allowed to push the 6 inside of the sum. So we could go ahead and push the 6 in. Usually, sometimes we take these things out. But here we actually have a reason to bring them in. And then I'm going to write this as -4 to the nth power times x to the nth power. So that is, I'm just distributing that, the fact that I'm raising stuff to the nth power, and I'm doing that individually to the x and to the coefficient, the number there. And so, right, the question is, what is maybe our c sub n? We have it written. So really, how I've asked the question, this would just be the answer to part B. But again, in web work, it'll quite often ask for the c sub n, right? And so let me just be very clear with this. This bit right here is the coefficient that's next to x to the nth power, right? And of course, right, once you have this too, this is quite powerful. You can actually figure out these other ones back here, right? So this, for instance, is c sub 0. This is the coefficient next to x to the 0. X to the 0 is, of course, 1. And so if you were to actually just plug in, right, n equals 0 here, notice that you'll get -4 to the 0, that's 1. Multiply that by 6, you get 6. If you wanted to know what the coefficient next to x to the first power is, right, we could figure that out. If you wanted to know the coefficient next to x squared, we could figure that out. And just by plugging that into my equation here. So this is actually quite powerful, but sometimes it's hard to kind of jump back and forth with this. So that's kind of why I just carry around all 3 pieces together at the same time. And then the last bit, what is the radius of convergence? Well, remember, we learned in 11.8, if you have a power series, you can figure out the radius of convergence by doing the ratio test. And this will always work, right? And so this is certainly an option. However, we learned a faster way when we have a specific function like this, just by using the radius of convergence for our known series. So in order to use this information in green, remember this series right here only works when the absolute value of u is less than 1. That is, the radius of convergence for u is 1, and it's centered at 0. So of course, we did lots of other things, right? Our u was defined as this here, and we want the radius of convergence for x, our variable. And so you can just say, well, plug in everywhere I see a u, I'm going to plug in my -4x. So -4x. And again, we're looking at this restriction here that the radius of convergence for u is 1. So the absolute value of u needs to be less than 1. And so if we go ahead and we just plug in, instead of u, our value there, the -4x, we can go ahead and apply the absolute value to the -4 and to the x. Then we can go ahead and divide by 4 on both sides. And we can find that the radius of convergence of x now needs to be, well, 1/4, right? So r is equal to 1/4 in our case. Notice, by the way, it's maybe not a coincidence that if you're thinking about, centering yourself around 0, you say, how far can I step away from 0, and still have your power series make sense? Well, notice that there is an asymptote. There's an asymptote when we plug in x equals -1/4. So if you were to step, to -1/4 from 0, that is, your radius is 1/4 there, you would hit an asymptote. And then that's going to be an issue there. So that's kind of a nice way to just double check, is that with these ones, the radius of convergence quite often has something to do with where the asymptotes are. Okay, I've been talking for a while. I'm sure there are questions. Let's go ahead and call on a few folks. Khalil, you have the floor.
Okay, so in the web work, they want you to find the C sub in first before you're able to move on to the finding what the series looks like, how you have that blue part. So I guess how would you do that? Or do you just want us to find the series and then work from there? Because when I was in the MLC, they showed a way that you could do it where you have to take the derivative of the function and then plug in 0 or something like that. But
well, that's coming up eventually. That's going to be called Maclaurin series, and that's 11.10. So we will be getting to that, but as of right now, we technically don't know that. And so I'm going to kind of show how would we do this in 11.9.
Okay, so then find the series first and then work through, because like I said, they want us to find the C sub n's first in 11.9.
Well, 11.9, I'm looking at the web work right now. I see that part 1 is compute some coefficients. Find the first 4 coefficients for the power series. So that's very similar to what we did for part A. And then part 2, what's the pattern in the general expression for the power series, right? And then that's where you figure out your C sub n. And then part 3, what is the radius or the interval of convergence?
Okay. And actually, I see now, because you have the 6 and then the 24, which would be your coefficients.
Exactly. So those were my answers for part A. And then part B, we figure out the C sub n. And then part C, we figure out the radius of convergence.
Okay, that makes sense. Thank you.
Yeah, no problem. Any questions in the Q&A, Yuan?
Someone's asking, is why we're representing the function as a series and instead of just using the function?
It turns out, right, that there's some functions out there that are very difficult to take derivatives or integrals for. And but infinite polynomials, or polynomials in general, right, are very easy to take derivatives or integrals for, right? The rules are very fast. And so maybe you're interested in some information about quite a complicated function where it's so difficult to take the derivative or the integral of. And really, this really falls more in the integral side of things. Derivatives are pretty well known and everything, but there are some functions that they actually don't have elementary antiderivatives. And so this is really the best you can do. And so that's kind of one great use for this sort of stuff, even though it seems kind of rather roundabout. Good. All right. Let's see here. Let's try another problem here. So this one, we have kind of some more difficult substitutions here. So I'm going to go ahead and rewrite this function. Oops. First as x to the 5th times 1 over 1 minus x squared. So we have this polynomial piece on top, x to the 5th. That's already a polynomial. It's already, again, we're trying to get this to look like an infinite polynomial here. So x to the 5th is already a perfectly good polynomial. This though, right, this is a reciprocal function. This isn't just a straight up polynomial here. And so we want to rewrite this bit in terms of its infinite polynomial. And so now when I'm looking at this, I'm thinking about, well, let's have u be equal to x squared, right? Because again, we're going to be using our good old formula here at 1 over 1 minus u is equal to 1 plus u squared plus dot, dot, dot. And if you wanted to write that in terms of sigma notation, right, this would be summing up from n equals 0 and beyond of u to the n. So we're going to go ahead and do that with this piece here. So again, the x to the 5th is going to be kind of along for the ride. We need to, this is already a polynomial, so it's fine as is. And then we're going to go ahead and substitute in, right? Everywhere I see a u, I'm going to put x squared. So we're going to have 1 plus x squared plus x squared squared plus x squared cubed plus so on and so forth, right? Again, everywhere I see a u, I'm putting an x squared. And then over here, again, this x to the 5th is along for the ride here. And we're summing up from n equals to 0 and beyond of x squared raised to the nth power. And so let's go ahead and take a line or so to simplify this down a little bit. Again, all of this is equal to our original function that we're tasked with finding power series information about. So just like before, right, I multiplied through by 6. Now I'm going to go ahead and multiply through by my x to the 5th. So I'm going to have what, x to the 5th plus what, this is going to be like x to the 7th, right? Because when I multiply x to the 5th times x squared, the exponents add. Okay, this is getting a bit more annoying here, right? X squared squared. Well, when you take x squared and you square it, right, that's x to the 4th. And then when you multiply by x to the 5th, this is going to become x to the 9th. Hopefully, if you were guessing, you've identified the pattern here. And you would probably guess the next one is x to the 11th, right? We seem to be doing a bunch of odd ones here, starting off at x to the 5th. And of course, you can verify x squared. If you cube that, you get x to the 6th. And then if you multiply by x to the 5th, you indeed do get x to the 11th. Let's go ahead and look at our sigma notation. By the way, if you wanted to, you could pause right here, right, and say, what are the first three non-zero terms, right? So the first three non-zero terms would be x to the 5th, or if you'd like to, you can really write down, you know, the coefficient there is 1, x to the 5th. And then here you have 1 x to the 7th, and here you have 1 x to the 9th, right? So the coefficients are rather boring for this one. They're just a bunch of ones, right? And so this might be our answer for part A, right? It asks, what are the first three non-zero terms? So of course, there's a bunch of zero terms, right? If I wanted to write this out, you know, and be very specific about even with the zero terms and everything, right? It would be 0 plus 0x plus 0x squared plus 0x cubed plus 0x to the 4th plus 1x to the 5th plus, right? So that's why you often exclude the zero terms, right? In this case, there's quite a few of them, and you don't really get anything interesting until x to the 5th. And so that's why they usually say non-zero terms there. So, okay, that's the answer for part A. And then for part B, again, we're looking at the sigma notation stuff. Just like before with the number 6, we push the 6 to the inside here. So I'm going to make this as x to the 5th now inside of our sum, inside of the sigma notation. And when we have powers raised to more powers, remember they multiply together. So this is going to become x to the 2n. Now, of course, we could simplify this down a little bit more because we have the same base, right? So this is going to be x to the 2n plus 5. Remember, when you have same bases being multiplied together, the exponents add. So you got the 2n plus the 5. And notice there's no really piece that has just numbers, right? All of the things have x's here, right? And so the coefficients are very boring. And we saw that, of course, right? That they're just ones. And so if, you know, Webrick asked for what is your C sub n, you would just say, well, it's a lot of ones, right? It's equal to 1. So, okay, that's the answer for part A and for part B. So I guess this right here is the answer for part B. Let me go ahead and start highlighting my answers here, just that way if folks are looking at this after class, they can see where the final answers are. And then part C, what is the radius R of convergence for this power series? Well, again, we could use the ratio test on this if we wanted to. However, it's going to be a little bit faster to set up this, right? The absolute value of u is less than 1. In this case, our u is equal to x squared. And remember, we can take the square root on both sides of an inequality, and that works out perfectly fine because the square root is an increasing function. So in this case, my radius of convergence is 1. And of course, right, if you're paranoid, you say, that seems a little fast, right? Well, first of all, yes, it is. It's nice. But also, if you wanted to double check and you had time, you know, right, you could use the 11.8 method. We have this power series. You could use the ratio test on this and verify that the radius of convergence is indeed equal to 1. Notice, by the way, here with these things, the radius of convergence only deals with the part, right, with this reciprocal function, the piece that you actually have to transform into an infinite polynomial, right? It doesn't have anything to do with this x to the 5th, right? This x to the 5th didn't have any, right? It was already a polynomial. And so, right, it doesn't really get included when you think about how do you transform it into a polynomial, into a power series here, because it's already a polynomial. And so really, it's only this piece here that deals with the radius of convergence. That's the piece that you have to transform into a power series still. And notice, just as before, right, up here, notice that this number 6 didn't play any role when it came to the radius of convergence, right? That 4 did down there, because that was part of the, you know, the reciprocal function and everything, but that 6 really didn't play any role. And so when you looked at kind of what does the radius of convergence equal, notice the 6 doesn't really appear anywhere in there, but the 4 does. And so, yeah, that's an important thing. All right. So let's go ahead and take a few questions if there are any. Anything going on in the Q&A that we should talk about, Yuan?
Do the first three non-zero terms include the x or just the coefficient?
As it's written here, when it says terms, you would include the x. So if it says, what are the first three non-zero terms, you include the x's. If it asks for the first three non-zero coefficients, then you wouldn't include the x's. Good. Why don't we go ahead and try one that's a little bit more difficult here. As we saw in the pre-class videos, not only can you do algebra with these power series, multiplying by stuff, rearranging, your classic algebraic manipulations, but you can also do calculus on these things, right? So that includes things like taking derivatives or integrals. So again, what we're starting off with here is that I have 1 over 1 minus u. This is the only thing that I know information about. And in particular, right, we're going to have 1 over 1 minus x in this case. I'm going to be taking some derivatives. So I'm going to go ahead and change it into this one here for the time being. Again, let me write this out as in all three pieces. So I'm going to do just this and then the sigma notation. And we're going to use this to create a more difficult, a power series for a more difficult function here. Here's where we have, it's not just 1 minus x cubed, right? But the entire quantity in the denominator there is cubed. And so there's no u substitution that we could do in order to make, what we have here look like where you have the entire quantity cubed. And so the best way to go about this is to take a derivative. So I'm going to take a derivative across the board. And so when I do this, well, for my normal function here, when I take the derivative of this, right, we're going to have -1 divided by 1 minus x squared. So I consider this as the reciprocal function, so as raised to the negative first power. When I take the derivative of that, the -1 comes down. So that's where that negative came from. I reduce my power by 1. So I get 1 minus x now being squared. And then I forgot one thing. Can someone tell me what I forgot maybe? When I took the derivative of this. So yeah, the chain rule. Chain rule, I have to take the derivative of the inside. And the derivative of the inside, well, the derivative of 1 is 0, and the derivative of negative x is -1. So actually this becomes positive, right? There's two negatives, right? The -1 coming down initially, and then when we take the derivative of the inside thanks to the chain rule. So of course, that's how we take the derivative of kind of our classic functions here. If you wanted to take the derivative of this infinite polynomial, certainly you could do that. And the derivative of 1 is 0. The derivative of x is 1. The derivative of x squared is going to be 2x. The derivative of x cubed is going to be 3x squared, so on and so forth. Moreover, we can even take derivatives in our sigma notation, and it works just as you would guess. So because we can take derivatives across sums, you just apply it to each individual piece. So when I go and I take the derivatives of the individual pieces, right, these x to the n's, well, according to the power rule, the n would come down and I'd reduce my power by 1. So notice, by the way, here we have 0, then 1, then 2, then 3. This corresponds to this n right here. When you plug in n equals 0, n equals 1, n equals 2, n equals 3, right? And notice that the power of the x's right next to that is always 1 lower than that number. So, right, here, if you wanted to, you could write this as 1x to the 0, 2x to the first, 3x squared. Right? So you get these changing numbers, and then the power of x is always 1 less than the coefficient there. Okay. And we had a pre-class video that was very, a pre-class video problem. There we go. It was very similar to this. But notice this one here wants a quantity x, the denominator there, 1 minus x all being cubed. So as you would probably guess, right, we need to take one more derivative. And so when I take one more derivative here, let's see, a -2 is going to come down. I reduce my power by 1. Then I multiply by the derivative of the inside, and this becomes +2. When I take the derivative kind of across the board here, well, the derivative of 0 is, of course, 0. The derivative of 1 is 0. The derivative of 2x is 2. The derivative of 3x squared is going to be 6x. And now at this point, I realize that, you know, for part A, we need 3 non-zero terms. I'm worried that I don't have enough of those, right? So let's maybe go back and interject one more here. So that way we have enough. I'm going to do x to the 4th. And this is going to be 4x cubed. And so now when I take the derivative of that, I'm going to have 12x squared. Okay, so now at this point, right, we can already see, right, we have 3 non-zero terms at least, so that's excellent. And on the right-hand side, when I take the derivative of this, well, again, we can take derivatives across sums. This n right here doesn't have any x's in it. It's along for the ride. Remember, we're taking derivatives with respect to x. And so when I take the derivative of x to some power, according to the power rule, right, that power comes down, and I reduce my power by 1. So I get something like this. Now, this is all well and good, and we have recreated, you know, the vast majority of our function here. But in my particular case, I wanted an 8 on top, right? And notice that there's a 2 on top here. And so now that we kind of know what the structure of it, you know, the main piece of it looks like, let's go ahead and change that 2 to an 8. And of course, the way that we're going to do that is by multiplying by 4. And again, we're going to do that on every single piece. So on the left-hand side, in the middle, so let's go ahead and maybe simplify a little bit. When I multiply by 4, we're going to have, let's see, 8, 24x, 48x squared, so on and so forth. And then lastly, we have summing up from n equals 0 to infinity of 4. Right? I'm going to push that 4 inside of the sum here. Notice that all of this stuff right here would be our coefficients. And then here's all of our stuff with powers of x. So again, we kind of want to write it down quite often in web work, just like this. So this right here, we now have basically all of our answers for part A. Here's what these look like. The first 3 non-zero terms. For part B, write this as a power series. We have that. And finally, for part C, remember we started off with this 1 over 1 minus x here. We know that the radius of convergence for this is that the x, right, has a radius of 1. Again, that nice theorem that we had says that when you take derivatives, that does not alter the radius of convergence. So all of this right here is not altering the radius of convergence. Multiplying by 4 is not going to alter the radius of convergence. So lastly, right, this remains unchanged. And so r is going to be equal to 1 in our case. All right. Yeah, there's a couple of hands up. Let's go ahead and call on some folks here. Again, this is getting more complicated because now we're comboing together some calculus along with this power series stuff. So let's see what kind of questions are out there. Robbie, I see your hand up first here. You got the floor.
Yeah, there was a part in the pre-class where I don't remember if you were taking a derivative or an integral, but you changed the sigma notation from n equals 0 to n equals 1. I was wondering what that was about.
Yeah, so in this case here, notice that if I was to plug in n equals 0, it would be rather boring, right? Because you're going to have 0 as this n right here times a bunch of other stuff. So this is going to be a 0 term. It corresponds to this first term right here was 0, right? And so the question is, well, do you really need to include that? And the answer is no. right? So we could turn this 0 right here to a 1 if we'd like, because, you know, whether you include it or not, that first term is just 0. So do you really need to add plus 0 to something? Well, no, that's not going to alter the end result if you don't add 0. And likewise, you can see here that in this case, because we've taken now 2 derivatives, we also don't need n equals 1, right? If we were to plug in n equals 1, this bit would be 0. 0 times a bunch of stuff, who cares, right? And so at this point, we also don't need n equals 1. So you could actually start off, and this corresponds to our second 0 right here, right? This is n equals 0. This is n equals 1. Here is n equals 2, so on and so forth, sort of deal. So really, you can just start at n equals 2 because that's where, you know, kind of the action starts. Everything that's non-zero happens at 2 and beyond. Does that sort of make sense?
Yeah, it does, but it doesn't really matter if you start at 0 or 2 in this case.
Correct. And in all the cases, right? I mean, if you want to be maximally efficient, right, you would start at 2.
Okay, thank you.
Yeah, no problem. Okay, let's go ahead and let's see. I haven't heard from Jeff yet today. Jeff, you got the floor.
Thank you, Professor. When you were taking the derivative the second time of the series, you brought the n down as if it was a constant. Is that right?
Yeah, whenever I take the derivatives, right, I don't know what constant it is, right? It corresponds to a lot of different things depending on what term we're at. But, you know, they are just constants, you know, first power, second power, third power, fourth power. And so when you take the derivative of it with respect to x, it just comes down and you apply the power rule just like they're constants.
Okay, thank you.
Yeah, definitely. A quick side note about this. I would not call this bit right here. This comes up in web work a few times. This is not C sub n. Right? So if it asks for what C sub n is, you can't say it's that because that's not the coefficient that's next to x to the nth power, right? That's next to the power of x to the n minus 2, right? And so if WebWork asks you for what is your C sub n, sometimes you do have to play this game a little bit of trying to figure out how would you rewrite this so that way you know what your coefficient is, right? That's next to the thing that's x to the n. Right? Because this, I mean, certainly it relies on n here, but the power here is a couple lower, right? Again, kind of this has to do with n equals 2 right here. And notice that this is next to x to the 0th power. And this would be n equals 3. And notice again, this is next to x to the first power, right? So the power of x seems to be 2 lower than maybe we want it to be. Likewise, here is n equals 4. So this isn't really the thing that's next to x to the 4th power. It's the thing that's next to x squared. And so there's kind of a fast way and a slow way to account for this. Oops, shouldn't have erased the x squared here. And I guess basically what I want to say here is that there's this trick you can do with re-indexing. So you could either kind of start with these numbers from scratch and figure out the series for this based on x sub n or x to the nth power, or you could do this trick with re-indexing. And so I'd like to teach you a trick for re-indexing this. So I'd like to add 2 to my n's. So that is, I'd like to rewrite this as x to the n here, right? Because I want to take this bit and add 2 to it. And you can do that, but you have to add 2 to all of your n's. So that is, we need to make this n plus 1 and 4 and n plus 2. So that is, we need to add 2 to all of our n's. So this n minus 1 becomes n plus 1. And then we have to think a little bit about where we should be starting, right? So before here, we started off at n equals 2. And if I had updated this, n equals 2 here. So when you add 2 kind of in all of these pieces up here, you need to subtract 2 from your starting point. So starting off at n equals 0 to infinity, because you do need that constant term. So let's be paranoid and just double check that this is just another way to rewrite. Again, we've changed our index a little bit, and that we still get this same series here. So now if I start off at n equals 0, let's see, I'd get 4 times 0 plus 2, 0 plus 1 times x to the 0. Well, x to the 0 is 1, and we have 4 times 2 times 1. This is going to be 8. So this right here is going to be the same thing as 8. So, okay, so far so good. What about if we do n equals 1? So I'd have 4 times 3 times 2 times x to the first power. So that is, I'm plugging in 1 everywhere I see n next. So 4 times 3 times 2 is going to be 24 x to the first power. So, okay, that seems to be working out well. And we could even try n equals 2 and see that that works out just fine as well. So now this would be a way that you could rewrite it. This is really the coefficient that's next to x to the nth power. So sometimes just doing these, by hand here, just expressing it as any old power series is a little bit easier than when you have to get it in a certain form. But of course, computer systems and whatnot, including web work, require you to get it in a certain form. And so that's why you want to know what your coefficients are that are next to the x to the nth power here. So that's just kind of a little bit on the side there, but you'll have to do this, I think, once or twice in the WebWorks. All right, let's take a few more questions here. Khalil, I see your hand up again. What question do you have for us?
I talked in the Q&A and kind of got answered.
Okay.
But so like, I just kind of missed the beginning of why we had to take the derivative of 1 over 1 minus x. I know you said it was something to do with the cube. Yes. In the original equation.
Exactly. There's no way using just substitutions with just 1 over 1 minus u. There's no kind of clever substitution that can replicate the fact that you have this entire quantity down here being cubed, right? If this had just been 1 over 1 minus x cubed, right? Well, yeah, we could let u be equal to x cubed and we, could go along our merry way. But the fact that you have this entire quantity being cubed, there's no way to really replicate that with just, substituting in for our u's. So we have to be a little bit more clever about how can we replicate this function right here, given only information about, things that look like this. And so in order to create this, quantity cubed in the denominator, the best way is to take derivatives. And so that's why we need to take derivatives for this one. And you can see if you take one derivative, you get this quantity squared. If you take 2 derivatives, you get quantity cubed.
Okay. And then you want that 2 to be an 8, which is why you multiplied by 4 throughout the whole thing.
Exactly. Yes.
Okay. Okay. That makes sense. Thank you.
Yeah, no problem. I don't know what I was writing too fast. This looks like derivate. All right. A little bit better. Let's see here. Riley, you got the next question.
Hi. So I was just wondering if you could explain again how you went from the n minus 2 being in like the exponent to it just being n.
Mm-hmm. So yeah, this is something that maybe computer scientists will be a little bit more comfortable with, where you kind of rename your variable kind of while you're using it. It's kind of like the whole like n equals n plus 1. I mean, that's a really weird math thing to do. In math, we would solve this and we would say, wait, 0 equals 1, right? But computer scientists, right, they kind of reuse their variables over and over again. So essentially, that's what we're doing here. This is technically a different variable that we just kind of renamed to call it n again, because that's what we use. But more formally, right, we could set, maybe let's use k's, right? So I'm going to say that I would like n minus 2 to be equal to k. So that is, I'm going to transform, instead of n minus 2 here, I would like to get, something that's a little bit cleaner than that. In this case, we're going to be calling it k. And so I'm going to replace that, right? So if I have this n minus 2, we're going to call that k. And so we need to kind of replace all these as well. So instead of n minus 1 here, well, I could add 1 to both sides of this, and I would get that this should be k plus 1. And likewise, in my other one here, instead of n, right, we could call this k plus 2. And when we do that, right, we're supposed to be starting off at n equals 2 down here. We need to know what is the corresponding k value to that. So if I was to plug in n equals 2 here, we would get that, we get k equals 0. So 0 is the correct thing to start at. So this right here is, well, why it's called reindexing, because we're fundamentally not changing things except for just kind of, the name. However, right, for all of our problems, we've felt more comfortable and we've just used n's the entire time. So once you make this transformation, you kind of go back and you, instead of calling it k, you call this n. And that's the kind of trick that, again, kind of computer scientists do quite often there. So this is one way to maybe a little bit slower to see why this works. Does that help at all?
Okay. Yeah, that helps a lot. Thank you.
Excellent. Yeah. Okay. Let's see. Do we have any questions in Q&A that we need to talk about you on?
Someone is considering like xn. Can you write as xn over x squared, and then can you say that's the cn? I'm not sure what cn is.
Oh, yeah. So you can't really, you need to combo all of your x's together in one piece. So this is clever, but this you would get nicked off on because this isn't a polynomial right here, right? So you're not allowed to have division by powers of x when you're considering polynomials. And so that's why you wouldn't want to write it like this. So unfortunately, I mean, it's clever, but unfortunately not. Let's call on a few more folks with raised hands and whatnot. I guess we are after 2:40, so this is going to be our last problem. We'll stick around, and take some questions and all that sort of stuff for anyone who has them. But otherwise, thank you so much for joining us. And if you have questions but have to leave, please post them on Piazza, and we'll take a look at those as well. So, all right.